All right. Hello, everyone. It's basically, if you're here, you're probably watching my video on YouTube, where I'm basically just going to do a walkthrough of basically chapters in the classical dynamics textbook. So, without further ado, let's go over chapter 1. So my kind of goal for this is kind of just, I'm doing this just to study, basically, and then if someone just wants to just, I guess, watch someone go through it. So the first chapter kind of details what kind of background mathematical knowledge you need for basically, classical dynamics and stuff. So first off, we're going to start off with the concept of a scalar, and you can see the, the table here stuff we're going to go over. Okay, so what exactly is a scalar? So 1.2, concept of a scalar. Well, the textbook basically defines it as quantities that are invariant. You're gonna see that word a lot if you take like special relativity and other stuff under coordinate transformations. And they give an example of mass, which is an invariant quantity. And here's kind of an example. We have all these, like you can think of it as like a crystal lattice or something, whatever you want to call it. And then we rotate our coordinate axis to be like this, x prime, y prime. And notice that the actual positions of these don't actually change. Like it's still in that, square shape. But it wouldn't really make sense if I looked at 2 and I evaluated the mass of 2 for the mass of 2 to be different, right? So basically how you would write it is mass of x comma y, like the mass function or whatever, is equal to x prime, y prime. In other words, where x prime and y prime are your coordinate axes. So and we'll get into how to rotate between them and stuff like that. And basically what it's telling you is that a scalar does not change. So it's just a number for that point. So yeah, now let's go into coordinate transformations so we can kind of see how we can actually rotate our axes. So 1.3 coordinate transformations. Okay, cool. Basically, let me just take the drawing so you guys don't have to deal with my terrible drawing skills. So what this is basically telling us right now is that we have some point P, which I'll highlight right here. And we have 2 axes. This is in 2 dimensions. We have the x1 axis, so the x-axis basically, the x2 axis, and then the y1 and y-axis. So highlight this in yellow, and then in purple. Purple's my favorite color. We'll highlight these. So we see we have 2 different coordinate axes. And the point P remains unchanged, right? But depending on what we're measuring it relative to, aka our axes, is going to change. So what this basically tells us is that we can basically find out what x1 prime is in terms of x1. Basically by summing up the projection of x1 onto the x1 prime axis. So how much does this go onto this, basically, and so forth. And you can see that the vector A. So we can come up to the equation x1 prime is equal to x1 cosine theta. So x1 cosine theta is this length right here. Let me draw that in a different color just so it's a little different. This length right here, that's x1 cosine theta, which we can see, right, because this is the angle theta. So then the hypotenuse is that one. So yeah, plus x2 sine theta. X2 sine theta. So again, let me draw this in blue. X2 sine theta is this right here, right? So let's move this over there and put it there, and we notice, boom, we have our new x1 prime, axis. I think I did that right. But okay. And then you can do a bit of mathematical identities to get this to x1 cosine theta plus x2. Remember, sine is just cosine phase shifted by pi over 2. Cosine of pi over 2 minus theta. Okay. And then again, similar analysis will give you x2 prime is equal to negative x1 sine theta plus x2 cosine theta, which again, you can just change the sign to a phase shifted cosine just to have it all in terms of the same sine and cosine. x1 cosine of pi over 2 plus theta plus x2 cosine theta. Okay. Basically, that's a lot of cosines, and the reason why we all want to get in cosines is we want to make our lives easier and not write a bunch of stuff. So we can kind of define the set of numbers, which we're going to call lambda ij, equal to cosine of x prime I xj. So in this example, like lambda, so lambda 1, 2 is equal to cosine of x1 prime x2, if that makes sense. Okay, because this kind of tells us the angle between the xi axis, xi prime axis, and the xj axis. So like, for example, angle between this and this. And that'll just help us standardize our math. So as an example, lambda 1, 1 is equal to cosine x1 prime x1, which we kind of already know is between this axis and this axis, right? Which we kind of already know is just theta, or cosine theta, sorry. And that's just equal to cosine theta, because it's cosine of the angle between them, which is theta. And the same thing, we go to lambda 1, 2. Well, that's cosine of x1 prime, comma, x2. Remember, I maps to here, j maps to here. And that's just equal to, well, cosine of pi over 2 minus theta, which is sine theta, which is the exact same thing we had right here. And then we can continue this, and you basically get lambda 2, 1 is equal to negative sine theta. Lambda 2, 2 is equal to cosine theta. So we kind of just defined basically 4 different functions kind of that basically tell us how our system will transform if we move from the non-prime coordinate axis to the prime axis. So we basically get some equations of transformation that tell us x1 prime is equal to lambda 1, 1 x1 plus lambda 1, 2 x2, and then x2 prime is equal to lambda 2, 1 x1 plus lambda 2, 2 x2. And feel free to verify for yourself that this right here is the same as the equations we derived up here. And now, if you've probably taken a higher math class or something before, you might realize this kind of looks like we're leading into something, right? Which I don't want to spoil it, but you probably heard of a matrix. And we can actually represent this as a matrix. But before we do that, let me show you the general formulation of how the matrix comes to be. So what this basically tells us, if we were to do summation notation, it tells us that xi prime is equal to the sum, j is equal to 1 to your dimension, 1, 2, 3, if you have a 3-dimension or 2-dimension system, of lambda ij xj. Where remember, I equals 1, 2, ... to d. So for general cases, this is 1, 2, 3. If it's 2-dimensional, you only go up to 2. And similarly, we can define an inverse transformation, which is xi. Remember, notice there's no prime, is equal to the summation of j is equal to 1 to your dimension of lambda j1. So notice the indices switch. Ji. Xj prime. So you kind of just flip the stuff around if you look above. Again, where I equals 1 to dimension, usually 1, 2, 3. Okay. And I guess now they tell us a name for what lambda ij is. So they say lambda ij is called the directional cosine of the xi prime axis relative to the xj axis. But now we have all these values, and you kind of notice you're always going to get basically a matrix representation. So we can kind of write the lambda matrix as 1, 1. I'll do it in 3 dimensions just because the textbook also does in 3 dimensions. But I'll show you how it looks in 2 dimensions as well as soon as I finish writing this. 2 lambda 33. And these are all defined as from the summation. And if we just wanted the 2-dimensional matrix, well, that's just right here. And you just cut off your matrix there. And if you don't know how to multiply matrices, don't worry, we'll get into that in a bit. But yeah, so basically lambda kind of defines our transformation matrix, okay, or rotation matrix. So let's kind of look at how it works for this point P again. And it's a lot of writing, so I'm actually just going to screenshot from the textbook the math for it because I think it'll save time. But notice we have our x1 and x1 prime axes right here are identical. Nothing changes. So the angle between them should be 0, right? Okay, x2 and x2 prime, so kind of y2 or y prime, y1 and y2. Angle is 30 degrees, and then we also have some angle here, right? Okay, so we could basically just put it into our above formulation, and we get these values. Where I want you to realize that there's no fancy math going in, as we kind of realized already, between x1 and x1, right here, 0 degrees, so we know cosine of 0 is 1. Between y1, y2, so x1 prime right here, and x2, well, that's just 9 degrees, right? It's straight normal. So all the ones with 1 should just give us 1 or 0 because it's on the same axes as the original axes. And then for the other ones, we see our 30 degrees, 0.866, which is cosine of 30, and then 2, 3, and so forth. And then when we want to go to the third axis, we can basically just add 90 plus 30 to get the angle we want, and so forth. So yeah, and we basically just can formulate all this in a nice little matrix, and this will tell us how we can coordinate transform if we want to move from the prime to the non-prime axis, or the other way around. What we see is if we put them into the actual formulation of lambda 1, 1, lambda 1, 2, lambda 1, 3, to basically solve for the x1 primes, or the x primes, we get 2, 2.37, 2.1. So we see this like the point P is different than what it was before in terms of the location relative to the axis, of course. But what we also notice is it wouldn't make sense for a coordinate axis system to change the magnitude of r. So what r kind of is called a position vector. Is if I have any coordinate axis system, let me just draw this down here actually. I have any coordinate axis system, I have a point here. R is defined as you start at origin, boom, that's your r vector. It just points straight to the point P, and we see that the length is unchanged here, depending on if you're using non-primes or primes. And that should kind of make sense because all you're doing is rotating your coordinate axis system so that r vector you draw the exact same, regardless. Okay, perfect. So now we can move into kind of 1.4, which is properties of rotation matrices. Okay, awesome. So basically, let's define some angles and stuff. So a little bit of geometry tells you that cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1, where the angles are above here as defined. And that's kind of like reminiscent of, I'm sure you guys know, like cosine squared. Actually, wait, no. It's just, that's just, what's it called? That might be from the log cosines. But anyways, I guess that's an identity they give you. And I guess they give you a problem 1.2 to prove this, which we'll see if I have time to do that. Probably not. But then we can also define a kind of theta between these non-prime and these prime angles. So kind of like the difference between them, if that makes sense. So that lets us basically write that, well, cosine of theta is equal to cosine of alpha times cosine of alpha prime, so kind of getting the cosine alpha squared, plus cosine of beta prime, plus cosine of gamma prime. And that basically tells us how the transformation is going to work from an angle perspective. So another property that we can kind of talk about is about the lambdas. So let's see. What they tell us is if we're working in 3 dimensions, there's 9 values, right, of lambda ij, like that. However, they're not all independent. Only 3 are dependent because 6 relationships exist among them. So 3 are independent, and I'll explain what that means in a second. Because the angle between the x1 prime axis and the x2 prime axis is pi half, if we go over to actually any axis like that is pi half because they're always orthogonal to each other, which I'll get into what that means. We can basically tell us, so basically between any axes, right, like if we have our normal axes, right, this is a right angle with that, this has a right angle with that, and this has a right angle with that, right? That's kind of what orthogonal means. But we can basically write lambda 1, 1, lambda 2, 1, plus lambda 1, 2, lambda 2, 2, plus lambda 1, 3, lambda 2, 3. And notice how the numbers switch. Well, that's just equal to cosine theta, what we have up here, which is equal to cosine of pi over 2, which is equal to 0. That's because 1, 1 and 2, 1 are orthogonal to each other. So what that means basically is, let me write this in summation notation, sum over j of lambda 1j, lambda 2j is equal to 0. Notice we start with 1, and then the next term, there's always a 2 here. We're basically saying anything between the x1 and x2, or x and y axes, have to be orthogonal to each other, so that if you multiply them together, you get 0. And that basically lets us generalize this to kind of the same thing, where it's lambda ij, lambda kj is equal to 0 when I is not equal to k, where you can kind of convince yourself this is like an extension in all directions for this. Basically what this is saying right here is that if I and k are equal, you're basically just doing like, lambda 1, 1, lambda 1, 1 again, which is the same angle, so it's not going to be 0, it'll give you 1. But if this one and this one are not equal, you're basically comparing the x1 to the x2, or if that's a 2, the x2 to the x3, if that's a 3, and so forth. And you're basically saying that there's basically 90 degrees between each x1, x2, and x3 axis, regardless if they're prime or unprime. Between like the primes. So the primes go with the primes, the non-primes go with the non-primes. And this kind of lets us basically, again, so we could go back to this equation right here. That basically tells us lambda 1, 1 squared plus lambda 1, 2 squared plus lambda 1, 3 squared is equal to 1, or the sum over j of lambda ij squared is equal to sum over j, let's just break it down, 1j, lambda 1j is equal to 1, which is kind of what I just alluded to up here, what happens if, what's it called? If the numbers are the same. So if I equals k, it's 1 basically. And now this is like a bunch of math, but this basically is a function, if you've taken other physics classes before, you might have heard of, which is the Kronecker delta function. So the Kronecker delta function, I don't know if function is the right word, they call it symbol, I always thought it was function, but oh well, which is basically delta ij, and it's defined as sum over j, or it's not really defined, this is just how they write it, lambda kj is equal to ik, where delta ik is equal to 0 or 1, depending if I does not equal k, and then if I equals k. There's a lot of cool symbols in math and stuff that we use a lot in physics. And basically, if stuff is mutually perpendicular like this, like the x and y axes always have 90 degrees between each other, and the x and x axis is always 0 degrees, we call the system to be orthogonal. Now that's a fancy word, but it kind of just means what's it called? You have it's just perpendicular basically. And this equation right here is the orthogonality conditioned. And there's a lot of cool things you can learn about, like other stuff, like stuff called like Graham-Schmidt, how to like orthogonalize a set of vectors and stuff. But we won't worry about that for this. But yeah. And also cooler symbols like the Levi-Civita symbol and so forth. But anyways, okay. So we've kind of established that lambda I, lambda ij, lambda ik is equal to delta jk. Notice, what I want you to notice here, this is kind of a bit out of scope for this class, but something I remember from my previous classes, is notice the difference between these two right here. Why are we summing over I and j, and then we notice that we just get the difference here is we get ik, difference here is we get jk. But they're actually saying the exact same thing, because since you're summing over them, you basically have freedom, and they're just dummy indices. Is kind of like how my professor used to like to say it, which means it doesn't really matter if you use an I or a J or whatever, because the meaning stays the same. And what we're basically doing here is you're summing over, and whenever you sum over repeated indices, this is something kind of that Einstein kind of formulated with the Einstein convention. I and I are repeated indices, so they go away, and then you get just lambda jk. That's just a little aside, not important for this class, just for the mathematical nerds out there. But anyways, okay, so that's all well and good. We've done a lot of, I guess, math, but why don't we get into our formulation for math, how we actually use this in practice. So let's say we have some point, which I guess we'll call x, and we can write that as either a column matrix, x1, x2, x3, which kind of looks like a vector, right? Or a row matrix, where x is equal to x1, x2, x3. But now what we kind of know, right, is we know that if we want to move like x into the x prime, right, we know xi prime is equal to sum over j of lambda ij xj, right? In other words, in the more general case, I don't really have bold because the textbook has bold, so I'll put a bar over mine, where like the bar is like the whole thing. X prime bar is equal to lambda. Remember, I'll put lambda bar, like the big boy lambda that has all the values of it. So this right here in matrix form, times x, like that. So what this basically tells us then is that I can basically rewrite this stuff like this: x1 prime, x2 prime, x3 prime as a column matrix is equal to lambda 1 1, lambda 1 2, lambda 1 3. I'll just write it out, I guess. 2 2, 2 3, 3 1, 3 2, 3 3. I'm gonna be kind of disappointed if it's not been recording this entire time. But anyways, x1, x2, x3. Okay, So basically we just rewrote this equation right here into a kind of matrix form, which kind of helps us remember how stuff multiplies and stuff. So it's going to be kind of hard to show you this, but actually no, it's not. I have a highlighter. So if I want to get x1 prime, matrix multiplication tells us, which we can kind of actually like backtrack and figure out by inspection because we know what x1 prime should be equal to. It kind of tells us we take this right here and we multiply by this, right? In other words, x1 prime is equal to lambda 1, 1, x1 plus lambda 1, 2, x2 plus lambda 1, 3, x3. And then, you can do the same analysis like that, and then you get these again or whatever, and so forth, right? And these are the exact same equations we had before. It's just a much neater way of writing it, right? And fun fact, computers are very good at multiplying matrices together. That's why actually computers are so useful. But okay, this basically tells us that we have a more compact way of writing it. So if you don't want to rewrite this all, you can always just do like, and you just mean this basically. Where the bar is kind of my pseudo notation. You can use whatever notation you want. It's supposed to be like bold or like capital. You can do that in like font or whatever, but whatever. But now the question is, I've kind of already given you how you multiply matrices together, but let's just say we have a matrix A, and then we have matrix B. So we want to know what AB is equal to. So let's say AB is equal to C. And then Cij, so the individual components of C, so remember I refers to row, J refers to column. Is equal to the product of AB ij. So I want C11, so C11 is equal to A times B 11, which is just equal to sum over K, A ik, B kj. Okay, so let's say we have, instead of writing this out, I'm just going to screenshot it now because I think it's faster. Let's say we have two matrices, A and B again, and there are these values right here. So when we want to multiply them together, we put them side by side, like this. And then C is equal to what happens when you kind of do the above formulation I kind of showed with the highlighter. So C is equal to, right, we take this, this, multiply it by this to get C11. So this, all the yellow just feeds into this right here. And then the purple is this with this, and it's right here, and so forth. And that's just kind of the way we multiply matrices together, and it's kind of useful. So I guess let's do one with just numbers, so it's probably easier to see. So let's say I have A and B again, and these are A and B, like that. And what I want you to notice is that, hold up, these ones right here were both square matrices. In other words, matrices are m by n. M and n were equal. But in this one, they're not. But it's still possible to do it. And that's because you don't need a square matrix to need. What you need is you're multiplying an m by n by an n by m matrix, basically. In other words, you just need these values to be the same. I think I said that right. But basically, what it means is, okay, this is a 3 by 3. So you have a 3 by 3, and you can multiply it by if it's a 3 by 2. In other words, these just have to be the same. And then the resulting is a 3 by 2. See? Hopefully that makes sense. But anyways. Okay, so those are kind of examples. Of how to multiply matrices, but let's get into a few more properties of them, which is the transpose, which basically tells us if we take our lambdas again, lambda transposed, I don't know why it's a lowercase t, I always learn with a capital T, but whatever, of ij is just equal to lambda of ji. So remember, these are values, so that means if we have like the 1, 1 component, it's equal to the 1, 1 component, right, because I and j are the same. And then if I take the transpose again, so lambda transpose, I should just get the same thing back, right? Because you just switch them and then you switch them back. So let's kind of look at how that works. or I guess I can just give you an example. I'll ignore what the textbook says and just do one of my own. So let's say I have a 3x3 matrix that goes like 1, 2, 3, 4, 5, 6, 7, 8, 9. So I basically want to swap all the rows of the columns. Transposed, that's equal to all the diagonals stay the same. 4, 2. So I swap these values. I basically just swap across the diagonal, if that makes sense. 7, 3, 6, 8. And that's the transpose. And you can verify that it keeps in mind with this formula right here. Now, the other thing that there is the identity matrix. Which is kind of like the number 1 in normal multiplication. So what it basically tells us is that if I multiply the identity matrix, which is kind of hard to write, they just have a bold 1, but I learned it as like that. 1A is equal to A, and then B times 1 is equal to B. So what this is saying basically is that it's just the matrix that you multiply to get back the same matrix. So for two-dimensional, basically it's usually going to be 1, 0, 0, 1 times A1, A2. Well, we multiply 1 times 0, so that's 1A1 plus 0A2, and then we have 0A1 plus 1A2, so these cancel out. So we get A1, oops, not divided by A2, and we basically get back A, right? Because that's A. So yeah. So we can consider basically the orthogonal rotational matrix lambda. So remember, lambda as a matrix is equal to lambda 1, 1, lambda 1, 2, lambda 2, 1, lambda 2, 2. Okay? And we can basically multiply by its transpose and see what happens. So lambda times lambda transposed is equal to, this is where screenshotting comes in handy because we're going to be here all day if I write this out. Which, if we do the math, is this right here. But since we know about the orthogonality relationships, namely lambda 1, 1, lambda 2, 1, lambda 1, 2, lambda 2, 2, 0, 0 as well, that basically tells us then that, oh, and these are all 1, right, because they have the same starting indices of 1 and 1, and then 2 and 2, so the i's are the same. We basically just get 1, 0, 0, 1. And this is a very special case because we just got the identity matrix. And that basically tells us that, I'm jumping the gun a bit, but basically that an orthogonal matrix, rotational matrix, basically their transpose is also their inverse. So the inverse of a matrix is defined as lambda times lambda inverse has to equal identity matrix, basically, or 1 is kind of how you think about it, right? Because, like, I don't know if you've done modular arithmetic or anything like that. That's how the inverse is defined. The inverse is anything basically defined. If you take the inverse of something, so A inverse times A always has to be 1 in any kind of math. Like, for example, so like 7 times 1 over 7 is equal to 1, right? Same with modular arithmetic, whatever. So basically, for orthogonal matrices, we have lambda transpose is equal to lambda inverse. And that's a very nice feature because you saw how quick it was to do the transpose, right? It's just like you draw your diagonal right here, and you just flip, and so forth. Okay. Now let's get into some bit more properties of matrices, which is just, I'll just go over them quickly. So matrix A times matrix B is not equal to matrix B times matrix A. Because remember, if I have a 3 by 3, I can multiply with a 3 by 2, but I can't multiply a 3 by 2 by a 3 by 3. Doesn't work. A negative 1 is equal to A inverse A is equal to 1. In other words, A commutes with its inverse and so forth. The identity matrix always commutes. Doesn't really matter. Matrix multiplication is associative, so ABC is equal to ABC, but, huge but, keep same order. You have to keep the same order or else it doesn't work for this reason above. Now, matrix addition, C is equal to A plus B. That's basically you just add up the elements. So Cij is equal to Aij plus Bij, and so forth. And addition only works if A and B are the same size, basically. Right, because then you wouldn't be able to add, like, the 9th element if B only has 6, right? Okay. So, okay. I'm just reading about the geometric significance of transformation matrices, which is the next topic, which I guess I can briefly go over it. Sorry, my handwriting is deteriorating because, I don't know, significance of transformation matrices. I have no idea how long this video is going to be, by the way. But okay. So they want us to consider coordinate axis rotated counterclockwise through an angle of 90 degrees as in figure 1.6. So let's pull out figure 1.6. So here's figure 1.6. This is what we're considering. What that basically tells us, it tells us x1 prime is equal to x2, x2 prime is equal to negative x1, and then x3 prime is equal to x3. So if we were to do the math of, you know, cosine of xi prime xj, we would get everything else is 0 but these two. In other words, everything else is 0 but the diagonal elements. Or no, not the diagonal elements, sorry. These elements. So our lambda matrix for this case, we'll call it lambda 1, is so 0, 1, 0, negative 1, 0, 0, 0, 0, 1. Basically, it's a lot of zeros and then basically some ones. This is a special case because we rotated by 90 degrees. Now let's consider a counterclockwise rotation about the x-axis, x1 axis, as in figure 1.7. So let's show that again. So notice we're rotating around a different axis this time. We want to see how that basically changes our matrix. So we can basically now write, in this one we have x1 prime is equal to, back to x1, x2 prime is equal to x3, and then x3 prime is equal to negative x2. Since there's no angles between them, right, we know we should only have basically 3 non-zero values in our matrix. So lambda 2, I'm going to call this, is equal to 1, 0, 0, 1, because, remember, the first element has to be 1 because they're the same, and then it's 0, 0, 1, so 2 maps to 3 now, and then 0, negative 1, 0 for our last value. And that basically tells us, well, let me ask a question. How can we get to, let's say we're at A. We're before we even rotated anything. So we're over here. Before rotated. How can we get to the end without just, like with one matrix or something like that? How can we just get to this result over here directly from here? Well, let's think about it. We know that x prime is equal to lambda 1 x. These are our matrices again. X double prime is equal to lambda 2 x prime. So then x double prime is equal to lambda 2 lambda 1 x. In other words, you can just multiply the rotation matrices together. So that tells us basically x1 double prime, x2 double prime, x3 double prime is equal to, if we multiply the matrices out together, 1, 0, 0, 0, 1, 1, 0, 0, x1, x2, x3, which is equal to x2, x3, x1. In other words, it's really nice because we can just multiply it all together. And we're done. That's kind of a nice property. In other words, lambda 3 is equal to lambda 2, lambda 1, where lambda 3 is this right here. But what I want to notice is, let's say we have a matrix called lambda 4, which is lambda 1, lambda 2. So we switch the order. If you do the math, which I encourage you to do so, you'll get a matrix that's 0, 0, 1, negative 1, 0, 0, 0, negative 1, 0, which is not the same as this, right? Again, order matters in multiply matrices, and so forth. Okay. Okay. I guess for the last part of this section, I'm just going to be talking about the useful matrices. Just matrices you see a lot. So in 2 dimensions, 2D, the lambda matrix, if you like just shift by an angle, is given by cosine theta, sine theta, minus sine theta, cosine theta. And then in 3 dimensions, if the same thing was true, lambda is just equal to, so the same lambda is just the same thing, cosine theta, sine theta, negative sine theta, cosine theta. But since z maps to z, you need a 1 down here, and then zeros, and then you just put zeros everywhere else. In other words, like x3 maps to x3 prime. But okay, these are just special matrices. See if there's anything else. There is more, but I guess I could go over determinant really quick as the last problem. Yeah, let's do determinant real quick. Okay. So last topic for this section is determinant of a matrix, which kind of looks like the absolute value. So let's say I have lambda. So let's say the determinant of lambda, which is just the same thing as like determinant of lambda, is equal to the determinant of, well, let's write out the matrix, y12, y21, y22. And what you do is you basically just say this is equal to this minus this. So blue minus red, which is the same thing as lambda 11, lambda 22 minus lambda 12, lambda 21. Okay. Now, it's a little bit more complicated in 3 dimensions. So in 3 dimensions, if I have, actually, I'll just write it out. I'll just screenshot it, I mean. In 3 dimensions, right, what you basically do is, it's kind of the same thing, but it's a minus plus minus thing. So what you do is you take this first value right here, y11, or lambda 11, and you say, all right, this value times this matrix right here. This determinant of this, the 2 by 2. So basically you just keep making smaller and smaller 2 by 2s. So if you have a 4-dimensional one, it's a lot more of a pain. I encourage you to do it once by hand and then just use a calculator. But you just basically need to get the 2 by 2 determinant or matrix, whatever, and you can just do it. So it's basically y11 times, again, let me do the same way, blue, red, and then it basically goes plus minus plus, like that. And then you can just see the formula over here. And that's how you calculate the determinant of a 3-dimensional matrix. And that's probably about as high as you'll have to do by hand, because it's not a math class. But yeah, okay. So that's it for our foray into matrices and stuff. That's kind of all the math I think you really need to know. And now let's go into 1.8, which is definitions of, that's such, I'm getting lazy, so I'm just going to screenshot it because it's a long, very long title. But okay, definitions of a scalar and a vector in terms of transformation properties. So let's consider a coordinate transformation of the type xi prime is equal to sum over j lambda ij xj. Okay, so that's just their normal transformation. And then we also know that the Kronecker delta symbol is active, which is lambda ij, lambda kj. Okay. So if under a transformation we have some quantity phi is unaffected, so what that means is phi in here is the same as phi in here. We call it scalar invariant, or just a scalar if you want. And then if we have some quantities like A1, A2, A3, this could be like a point or something. AI prime is equal to J lambda ij aj. In other words, we just plug it into here. And then this right here, A is a vector, and it's defined as A1, A2, A3. That's a row vector, but it doesn't really matter. But okay. So let's get into basically some elementary, that was it for that section, elementary scalar and vector operations. So, scalar and vector operations. This is a long section. Okay. So let's just screenshot the laws and I'll just talk about them. So we have addition and multiplication. I'll just screenshot this and talk about the textbook. Oops, right here. Okay. So addition tells us AI plus BI equals BI plus AI. In other words, the order of which you add stuff does not matter. Remember, A and B are vectors. Vectors, and then phi, psi, and oh Jesus Christ, I don't remember what that is. Whatever this is, it's I forget. It's something, but whatever. I'll call it squiggly. It's not squiggly, but whatever. So basically, commutative law holds, associative law holds. So a lot of our laws hold. Commutative law holds. Like for our addition, all of our laws hold. And then if we multiply something by a scalar, a vector by a scalar, so if I have a vector like 1, 2, and I multiply it by 2, that's the same thing as the vector 2, 4. You just multiply stuff, but it's still a vector. But if you multiply a scalar by a scalar, so like 5 times 4, well, it's just 20, right? Like you have two masses, right? Multiply the masses together, you still get a mass, which you'll see in like stuff like universal law for gravitation. And then we can prove 1.49 right here, and we see that it remains a vector. So yeah, okay. Now we can move on to 1.10. 1 second, I got a text to reply to. Okay. And 1.10 kind of tells us we're going to talk about the scalar product of two vectors. And there's multiple ways to write this. And multiple ways to describe it. So scalar product, I think, is the more general way of saying it. But you might have also heard a term called the inner product or dot product. Okay, so the scalar product is A dot B, hence the name dot product, which is kind of, I think, how most people learned it originally, is equal to sum over I of AI, BI. And we'll get into how you do this just to make it more clear. Sometimes called the dot product. It can also be written as, in some math places, inner product like that, which is the same thing as A dot B. But anyways, what this basically does is we basically want to find, well, this, by the way, will give us a number, aka a scalar. So let's say we have some vector A with A1, A2, A3. All right, I'm going to start drawing vectors with arrows above them so you know they're vectors. And let's say I want to find the magnitude or length of the vector. So I have my coordinate axis system. I have this vector right here, A. Okay, and I want to find basically what is the length of this, right? Remember, my vector is again defined in the projection across the, let me just write them out. X1, X2, that should be a 2, that should be a 3, that should be a 1, sorry. It's again defined as like how far you go this way, how far you go this way, and then how far you go this way. Okay, and that's how you get A1, A2, A3. Those are the projections across the X and Y and Z. So if I want to find the length, I just write the magnitude of it. Well, that's equal to, well, we have a nice little equation, which is the quadratic formula, or not the quadratic formula, Pythagoras theorem. A1 squared plus A2 squared plus A3 squared. And that'll give us the value. And that's defined as the length of A. But now let's say we want to find the, like for A dot B. we can write A dot B is equal to, these are vectors, these are magnitudes, over AB. So let's say we want to normalize it, basically. What that means, basically, is we take the dot product and then divide by their total length. Well, that's just the same as the sum over I of AI over A. In other words, the normalized of the individual parts. In other words, we can basically derive an equation that you guys have definitely seen in your lower division classes, which is, this tells us then that A dot B, oops, let me write this neater, sorry. Getting sloppy, over B is equal to, over I, capital, I guess they're doing capital lambdas, okay. IA, oh, Jesus. Oh, IB, where these right here are the directional cosines of the vectors, which, if you remember correctly, is what we were talking about a while ago. And that basically tells us then that this right here, remember, just goes to the cosine of A and B. Cosine between A and B. So that tells us then that A dot B is equal to magnitude of A, magnitude of B, cosine between them. So this means cosine between vectors A and vector B. Let me draw the vector arrows, actually. So let's draw a little picture. I think pictures have always helped me. Okay. I'll use an existing picture and actually draw on that picture to make it better. So let's say I have vector A here, and then I want to add vector B, and I'm going to draw vector B like this. So it's actually in the same plane, but it differs by this angle right here. It doesn't have to be in the same plane, by the way, theta. Then basically cosine of AB, let me draw B, cosine equals cosine of theta, sorry. Like that. And that's kind of what that's telling you. The dot product, if we can see here, right, we know, well, magnitude of A is a number, or scalar. Magnitude of B is a scalar, and cosine just always gives you a number between -1 and 1, right? So it's also a scalar. So that means this equals scalar, and that's why it's called the scalar product. Okay, and let's just, I guess, screenshot this little derivation so we can kind of see as how we can show that it's a scalar, basically. So A and B transform as vectors as, you know, AI prime goes to lambda AJ, right? Same with B. So then if we do A prime dot B prime, we just get the summation of them, and then we get a summation over some, what's it called, transformations. And then if we rearrange them, we basically see the magnitudes, because these are just numbers right here, pop out. And then these right here is the delta symbol, right? It's the Kronecker delta symbol, because if you sum over I, the i's go away and you get Kronecker JK. And then we see this right here. So then this, but now this is kind of where knowing your Kronecker delta symbols matters a lot, and how these work is we have a sum over J and a sum over K, right? Notice both of those are inside the Kronecker delta symbol, right? But remember, Kronecker delta, lambda JK, is always equal to 0 if J does not equal K, right? So that means what this basically does is it allows us to just delete this, and it just takes it away, basically, because whenever J does not equal K, so let's say K is equal to 1, and if J is equal to 1, then you just basically get AJ BJ sum over J. So I'm trying to think of a better way to explain this, but that's kind of like the point. So I guess we'll do numbers. Let's say J is equal to 1, 2, K is equal to 1, 2. So if J is equal to 1, right, then K can either be 1 or 2. When it's 1, we just get A1, B1, right? When it's 2, when K is equal to 2, we just get 0, because this gives us 0. And then when J goes to 2, we get, if K is equal to 1, we get 0 plus A2, B2, like that. And then what you notice is, well, we're just summing the multiplied version of the elements, which is the definition of the dot product. So it's just the sum of basically like 1 goes to 1, add 2 goes to 2, add 3 goes to 3, and so forth. I don't know why I erased all that. That was an accident. But anyways, okay. And that basically shows us that in any coordinate system, it doesn't matter. A dot B equals A dot B. Like A dot B prime equals A dot B. Okay. Now, because this value is unchanged, basically, so it's a scalar invariant, we can define the position vector, which is the point from the origin, which I kind of already alluded to. So let's grab a little picture real quick. Actually, that's for subtracting. We'll ignore that for now. We basically define the position vector as square root of A dot A, which, remember, is what I said was the distance when I drew the R vector, right? It was just, I said it was from, what's it called? Pythagoras, which it kind of is. It's kind of like an extended higher dimensional version of Pythagoras, right? Because if you're in 2 dimensions like this, I draw my thing like this, and we have 2 lengths, right? X and Y. How do you get C? Well, it's, you know, let's call them, let me write, A and B, it's just C is equal to A squared plus B squared square root, right? So it's kind of the higher dimensional version of that. We can immediately see that comes out from the dot product, right? But anyways, so now what we can do is, well, that's great. We know how to add vectors, kind of multiply them. How do we like subtract vectors? Well, let's look at a drawing. So drawing pictures in physics is the most powerful tool. So if you don't have to be artistic, like clearly I can't draw, but I still like to because it helps you kind of visualize things. So I have 2 vectors, A and B, and I want A minus B. Well, that means I start at A and I go to B basically, right? And that's A minus B. So we want the position vector from here to here. So from here to here. And that's the difference between A and B, right? So that basically lets us know that we can just get the distance, because the distance, remember, the dot product gives us the distance. So we can just basically get the distance between them and we're done. Using the exact same formulation as above. Okay. And here's just some laws in terms of commutative and distributive for dot product. So A dot B is the same as B dot A, which you can actually, because it's a number, it doesn't matter. Because remember, A dot B is equal to magnitude of A, magnitude of B, cosine theta, like the angle between them. Well, if I switch B and A's order, does it matter? No, because 5 times 6 is the same thing as 6 times 5, right? Okay, for addition, we see it distributes and then, yeah, we see it's like the same thing as just doing it like that. Because again, you're just getting a number. That's why. Okay. Now we can move on to, this is going to be a long video, 1.11, which is unit vectors, which is a very important concept, especially when describing vectors and stuff, because you want to kind of know a way that something points. So a unit vector is basically just a vector that has length equal to the unit of length used. So basically a unit vector will always have a value of 1, length of 1. For whatever unit your coordinate system is using. So what we can kind of look as is, let's say we have a vector r. Okay, we have the unit vector E sub r, where E just kind of is defined as like unit vectors. Well, I want basically the unit vector r to point in the same direction as r, but be length 1. So I can just do r, which is a vector, remember, divided by the magnitude of r, right? And that just gives me a length of 1, and it points in r, right? In other words, r R, ER, A is equal to R, like that. Okay, so the most common ones are I, J, K, you might have seen it in physics or engineering classes, E1, E2, E3, or R hat, theta hat, phi hat, which is what happens when we go to polar coordinates. So let's say I have a vector A. A is equal to A1, A2, A3. Okay. Oops. And then that means A is equal to E1, A1 plus E2, A2 plus E3, A3, or sum over I, EI, AI. And then you can do the same thing with I's and J's and so forth. Now, I's, J's, and K's, and R, thetas, and phi's, I think I like more. But a lot of times in textbooks, you'll just see the E's instead being used because we can do neat stuff like AI is equal to EI dot A, which basically just kind of breaks apart into this right here because it's indexed by numbers, right? And then you can get the first component, the second component, the third component, and so forth. So we already know that. So what we do know is that 2 unit vectors, so if any 2 unit vectors are orthogonal, so if orthogonal, EI dot EJ, so I does not equal J, or else it'd be the same vector, right? Has to equal the Kronecker delta symbol, and that kind of should make sense to you because let's say I have the coordinate axis like this, x1, x2, x3, and then I have the 3 vectors defined like that. These are my E vectors or whatever. Well, if I do a dot product of these two, right, which the dot product kind of tells you how much of your vector is projected onto the other vector. If they're at 90 degrees, cosine of 90 is 0, so you just get 0. So that's what the Kronecker delta kind of tells you. So, okay. I'm going to skip over the example they give you because it's just plugging in numbers into these equations. But now we kind of saw, well, we know that there was so if you multiply 2 vectors together, you get a scalar. But then how do you get a vector? Well, there's 2 ways to multiply vectors. And the second way is the cross product, or the vector product. So the vector product, so 1.12 is vector product, is defined as C, where C is a vector, is equal to A cross B. Okay? And thing to note, A cross B is not the same as B cross A, and we'll see why. Oh, they do tell us levy speed is symbol. Excellent. Okay, so what this basically tells us is that Ci, so the component of C in the I direction, so 1, 2, 3, is defined as the sum over jk of I, jk, aj, bk. Now you're like, oh crap, another symbol I have to remember. Well, don't worry, this symbol is not that bad. Basically, it tells us that, I'll just screenshot it because I want to write it out, but I'll tell you how I remember it, and then, because permutations, not everyone's taking probability or whatever, and you guys might not be super familiar with it. And basically, let's say I, j, and k. So you could have basically 1, 2, 3, 2, 3, 1, 3, 1, 2, or you could have 2, 1, 3, 1, 3, 2, 3, 2, 1. So these are even, these are odd. So the real way how you're supposed to do it is IJK form an even permutation of 1, 2, 3. So you start with 1, 2, 3, 0 is an even permutation. And then let's say you swap 2 and 1, so you get 2, 1, 3, and then you swap again, so you swap 1 and 3, so you get 2, 3, 1. Well, that's two swaps. That's even, right? So that's how you get 2, 3, 1, and so forth. And notice when I only did 1, I got 2, 1, 3, which is an odd permutation, which is -1. Because I only did 1, and so forth. I don't really like remembering it that way because I find that confusing. So what I actually do is I just write 1, 2, 3, because I know 1, 2, 3 is my starting point, and then I just make a cycle. I just move the 1 over here. So I get 2, 3, 1. And then I move the 2 over here. So I get 3, 1, 2. And these are all even. And that's because the Levi-Civita symbol is cyclic. Oh, they actually do explain this. Okay. My bad. I kind of jumped the gun here. But so this is how they explain it. And I basically just do cyclic permutations. Are always even like that. And then what you do is you just choose one that's not here. And then you just do cyclic permutations of that. And that's how you get odd. And that's just how I kind of remember it. So remember, even is +1, odd is -1. And that's how we kind of get the values. So this basically tells us, let's say we do, so using this notation, we kind of define the cross product or the vector product. So if we want the first value, right, we set I equal to 1, and then we get 1, 2, 3 plus 1, 3, 2 because everything else is 0. Because if you have any repeated indices, you get 0. So then we just get A2, B3, A3, B2, and so forth. Now, I wonder if they show you the easier way of doing the cross product. They don't. I'm going to show you it because it's much smarter. Let's say I have two vectors, A and B. A1, A2, A3, and then B1, B2, B3. So what you do is you say A cross B is equal to the determinant of I, J, K, A1, A2, A3, B1, B2, B3, which we know is just equal to I times A2, B3 minus A3, B2. Okay, I want you to look at this right here and tell me if it looks a lot like this. Well, it does, because it's the same thing. And remember, I is just our version of like the first component, right? C1. It tells you like the component of C in the X direction or the I direction, whatever you want to call it. And if you just remember how to do determinant, you don't have to memorize all this. But I just find this way a lot nicer and easier. But okay. So now that we know that, what does it tell us? Oh, okay. And then they have a derivation of, you can actually say that this A cross B is equivalent to C equals AB sine theta, which I guess I can put up for a second. So we're considering the expansion of the quantity, AB sine theta AB is equal to AB sine theta squared. So they expand it, and what you basically see right here is you get the cross product, right? So therefore, AB sine theta squared is kind of just like the magnitude. It tells us the magnitude of C squared. So the problem with this is it does not tell you the actual direction. It just tells you the length. Which you learn about the right-hand rule and all that later. But basically, if I have two vectors, and I want the cross product between them, you can get a vector that's perpendicular to both of them. So it's going to go like that, like into the page or something like that. But anyways, we'll get to that when we need to. So let's see. Oh, I guess it's also worth mentioning. Again, let's go to two dimensions because it's easier to like visualize. I have two vectors again. Oops, it's bad drawing. Sorry. Okay, I have two vectors like this. I have some angle between them, right? Well, if I extend this into a parallelogram, so I put blue again, like that, and then I put red again, pretend they're like the same length and everything, I just can't really draw. A cross B is just equal to AB sine theta, right? Which is also equal to the area of the parallelogram created. If you're confused by this, which I know is very hard to understand the first time you see it, I highly, highly, highly recommend 3 blue, 1 brown on YouTube. He has an amazing video on basically all the stuff you need to know about linear algebra ever, and I highly recommend that. But he goes into this, shows some fancy animations, which I do not know how to do. But yeah, okay. Another thing is they ask you to show. I won't do this now because for the sake of time, I'm kind of tired. It's just an example problem to go to. You can prove this identity. So yeah. But okay. Let's skip the examples. Okay, I'll also just another example. I'll just mention some other important properties. Again, I'm not going to run through the examples because if I did, this video would be 3 hours long. Which this is kind of more so learned in math classes and proved, so you don't really need to know how to prove this. At least I don't think so. So if we look at the indices, we noticed I goes to L, J goes to M for the first one, and then you kind of just cyclic it. So I goes to M, J goes to L, like that. That's a sum over K. The reason why is because if you sum over K, if you ever sum over a variable, that variable does no longer appear. That's like the Einstein summation convention, which you're free to read about in your own time, I guess. But yeah. Okay, and here's kind of the table of identities that's useful for cross products. Oh, they do tell you the matrix form. So, in case you guys thought I was making that up about how to do the vector product, that's how you do it. They used E1, E2, I3. I used the J's, IJK. Who cares? But here are a bunch of super useful vector products, which you can prove actually with basically just clever Levi-Civita stuff. And there's a really cool tables online and stuff that show you all that stuff. But for the sake of time, let's move on to 1.13. And sorry for this really long video. I really thought I could do this in under an hour. So my bad. But okay. So we want differentiation of a vector with respect to a scalar. Okay. So remember, phi is equal to phi prime because it's scalar invariant. S is equal to S prime. D phi has to equal to D phi prime, right? Like, if phi is the same in both coordinates, the derivative should be the same too. So d phi ds is equal to d phi prime ds prime, which is equal to d phi ds, and then make it prime, right? So we can basically define the differentiation of a vector A with respect to a scalar S according to basically the formulation we've derived. So remember, AI is equal to your rotational thing times your original component. So when you differentiate right here with respect to a scalar, you basically are differentiating that above equation. And you notice that means we can just do the summation and then differentiate with respect to the original component. But since S and S prime are identical, we can basically simplify it to this right here. Okay, so we don't need to change S prime because it's the same thing. But okay. So therefore, the quantities dA, J, and ds transform as do the components of a vector, and hence are the components of the vector, so we can write as dA over ds, where A is the vector. Now, if we were to, go back to your first ever calculus class, you thought you got rid of this equation. You did not, unfortunately. We could take the limit, it's like kind of the definition of the derivative, is the definition of the derivative, actually. And we can basically see what's really happening. In standard fashion, right, you take the little delta S and you see as it goes to 0. And we can kind of see how it's changing. So the derivatives of vector sums and products obey the rules of ordinary vectors of calculus. So what that basically means is take the derivative of that. Well, that's just the same thing as, doing it individually for right here. Dot product, again, it kind of looks like it's A dot B, so it looks like chain rule. It is chain rule. Again, chain rule, and then chain rule again. Right? Because this is with respect to a scalar. Basically, all this is telling you is that all the calculus you've learned so far applies again. So we can now go to examples of derivatives, velocity, acceleration, very important one. Examples of derivatives, velocity, and acceleration. Okay, so we know that V is kind of defined as dr dt, where r is, remember, just your position vector. So it's position over time, right? So r prime, where the dot, by the way, signifies a time derivative. That's just kind of like common notation physics. Where r equals r of t. And then same thing for the acceleration, the second time derivative of r. So in rectangular coordinates, aka our standard Cartesian coordinates, we can kind of write this as this, and we see that stuff gets kind of messy pretty fast. So we actually don't work a lot in rectangular coordinates when we're dealing with, well, it depends on the symmetry of the problem. But for now, just realize that r is equal to x1e1 plus x2e2 plus x3e3, and then we just take the derivative. It's just the derivative of each individual component, and same thing for the acceleration, right? But let's say we want to go to plane polar coordinates. So we want to move to polar. Now, polar coordinates are, you know, the less fun coordinates for people who are starting out because we're so used to the Cartesian coordinate system, but it's all basically the same math. So basically, if we want to find the change in ER, remember ER is this vector right here. Well, that's ER2 and ER1. So the change in them, right, is just we have our vector. We have our first, so ER at one point, ER at another point. Our change in it is just the difference between the vectors, right? We can kind of define that as DER. Same thing with theta. We have right here, right, we have our E theta 1, E theta 2, and then our DE theta right here. And we see the change in theta right here, so forth. Therefore, we can write that DER is equal to D theta E theta. Yeah, I don't know. That's no reason to write that. So basically, we can write from kind of inspection that the time derivative of ER is equal to the time derivative of theta, E theta, right here, right? Or E theta time derivative, sorry, is equal to negative theta time derivative ER. Right? So that means V, I don't know why I'm writing in red, sorry about that, but V is equal to dr dt, which is equal to d dt of r er. Remember, er is the unit vector, r is the actual vector. So that's just equal to r er, so r dot plus r e dot r, or v is equal to r dot, which is equal to, this is a vector, by the way. Oh, this notation gets confusing because it's kind of hard to write stuff, and so let me draw it this way, like that. So r vector dot is equal to r dot, so the length basically, plus r theta e theta, like that, where the only vector is right here. So basically, we're taking the derivative vector, and we notice it depends on multiple properties because we have the chain rule. Then same thing with the acceleration, we can do that as well. Right here, because we're just taking the time derivative of that. Notice that these are not bold, which means they're just numbers. If they're bold, I'll draw an arrow over them, and we can kind of see how it simplifies to, and we basically get the acceleration. So just in some other coordinate systems, because Cartesian, which is rectangular, it's not the only one. Spherical is similar as well, and then cylindrical is the last one. So you'll see spherical a bit. Cylindrical is very rare unless if you're working with like a coaxial cable or capacitor or something like that. Like where the geometry is a cylinder, then you'll see cylindrical. But other than that, it should be fine. Okay, so we basically see we have different ways of differentiating stuff. But okay. Okay, now we can move on to the concept of angular velocity, which you've probably learned about in your lower division classes, where omega, right, is equal to d theta dt, which is just theta prime, right? But v is equal to r d theta dt, which is equal to r omega. Or in other words, since r is equal to r sine alpha, let me show you what I mean from the drawing. That lets us write that v is equal to r omega sine alpha, where alpha is this vector right here. Because lowercase r is almost always defined as the vector from the origin pointing to where you currently are. So that lets us know that v is actually equal to omega cross r. You probably have memorized in like lower division classes that v is just equal to r omega, but it's actually the cross product between them. So, anyways, which should kind of make sense because v is pointing in this direction, right? And r is pointing in basically like below, right? So like that, as it's drawn. So omega is actually perpendicular to both of those, right? Because omega is like counterclockwise, right? It's this way. But yeah, okay. And then you can do this infinitesimally. We'll skip that. Okay, I think that's probably, there's some explanation about how you can derive it differently, but let's move on to the gradient operator, which is a very useful operator. So the gradients, this symbol right here. So let's say we have a coordinate transformation of phi prime. So we have, remember phi is a scalar, phi prime of x1 prime, x2 prime, x3 prime is going to be equal to phi of x1, x2, x3. Okay. So if I take the partial of prime with respect to the coordinate axes, right? J, it's just the partial with respect to j, and then prime. In other words, this is just, we're just refactoring this, right? Is equal to, sorry. And we know that the inverse coordinate transformation, xj is equal to lambda over k, lambda kj x prime k. So we just flip them from the original equation. So we can differentiate. And we basically get that the Kronecker delta symbol comes out again. So this right here is just equal to our rotational operation that we already had. So that simplifies things a lot, right? So then we know then that, let's conclude that if we go from here to here, we just see that this pops out again. And now we can define the grad function because phi was an arbitrarily scalar function. We can define the gradient operation, which is grad with respect to I is equal to, this is the grad symbol, which is just del xi, aka the partial derivative. Kind of the partial derivative, actually. It's the partial derivative of a component. So the grad vector is like kind of the partial derivative with respect to all components. So then what this means basically is I, ei, del xi. So it's actually a vector. It's like you take the partial derivative with respect to, you know, I, j, or k, and then you multiply it by that actual direction. So it has a direction. So we can basically define three things with respect to this, which is the gradient, divergence, and curl of vectors. If it'll screenshot. Let me re-screenshot because it's not working. Okay. So we have the gradient of a scalar function is just that grad phi, which is just what we defined above. And then we have the divergence of A. A is the vector again. It's you just dot the two together because remember the because the gradient, remember, is still a vector. And then the curl is you cross them. So the divergence basically tells you, again, 3 blue, 1 brown, fantastic video on this. The divergence basically tells you how much something diverges at a point, so how much it points towards it or not. And the curl tells you literally how much the vector field curls at a point. Okay, so if we want to really know what the gradient of a scalar function is, we can kind of look at this right here. So we have some vector field or whatever, which is represented in a map like this. And we can kind of see how phi actually works via a contour map, gradient of phi, sorry. Or we can see the intensity and strength of it, right? So we see the peaks right here. 0.9, that's a big boy peak. We can read these are maps of equal equal potential. It's the most here versus where it's flat, it's almost basically 0. And that's kind of what the divergence tells you. It tells you how much it changes with respect to your surroundings, basically. And I guess if we have the components of a vector, ds, so s being your usual length coordinate. Okay, I can't screenshot. Okay, I can actually. Never mind. Cancel. That's fine. Anyways, so if we have ds is equal to basically dx1, dx2, dx3, because s is just your length vector, position vector, displacement vector. Jesus, that's what it's called. Your d phi is just your gradient operator of phi dotted into ds. Okay, this lets us define another term where if we basically think about the maximum value, I'll just screenshot basically the entire page. So the maximum value of d phi occurs when gradient phi and ds are in the same direction, right? Because they're dotted. So I spoke about, again, before that the dot product kind of just tells you how much does A point in B, right? Because, again, it's the cosine angle between them is what matters. And if the angle is 0, that's when cosine's at maximum, right? So that basically tells us then that d phi max is equal to, basically you just multiply them together. In other words, that phi max is equal to d phi over ds. So therefore, we can say that the gradient of phi is in the direction of the greatest change in phi, which is kind of what I was trying to show with the contour map here, because the greatest change is at the peak, right? The vector has the maximum, the vector grad phi has the direction of the maximum change in phi, because any direction in space can be specified in terms of the unit vector n, where n is the normal vector. The rate of change of phi in the direction of n can be found from, you just dot the two, because that can give you the direction, right? So the successive operation of the gradient vector. So what happens if you take the gradient of the gradient? Well, that's just kind of taking like the second partial derivative of it, right? But you get rid of the directionality, right? Because E1 dot E1 is just 1, right? So that's called the Laplacian, which is just written as right here. And we can take the Laplacian on a scalar, and we just get basically the second partial derivative of it with respect to all directions. And you'll see this a lot in like quantum mechanics and stuff like that. But okay, let's move on to 1.17, which is the integration of vectors. So I apologize about this long video. We're almost done. I did not realize it was going to be this long. Not that I expect many people to watch this. But anyways, let's say we want to integrate some vectors. So we have vector A, dv, aka over a volume, because it's a three-dimensional vector, is A1, dv, A2, dv, A3, dv. Okay. Now, that's over a volume. What about if we want to integrate over a surface? So if we want to integrate over a surface, right, we can draw like our little differential area element, right? And when we do, we see that its direction is normal to the surface for the dA element, because when you, what's it called? dot the two, because it's given by the dot product a dot dA. Well, you want to basically find the angle between them, like that. Okay, so it's defined as over a surface of just a dot dA, and you take the integral of that. So therefore, that tells us dA is equal to n dot dA. Oh, sorry. dA is equal to, so where a is the vector, is just the vector n times dA. So then the integral of a dot dA, vector over the surface, is equal to, that's an a, sorry, is equal to the integral over the surface of a dot n dA. Or in other words, that a dot dA is equal to the integral of the surface of the sum of just your components, like that, because that's what the dot product is, right? Okay, so another, I guess, if we want to do like a line integral, so a line integral, right, is around a closed surface, or sorry, is along a path, which basically tells us it's kind of the same thing. So if we have a path from B to C, we can take our vector a dot ds, and that's just, again, you just multiply the components, right? Because that's what the dot product is defined as, and that gives us the line integral. And now we can use Gauss's theorem or Stokes' theorem if you're working on line integrals, which tells us that the integral over a surface of two things dotted into each other, two vectors dotted into each other, is the same thing as the integral of the volume of the divergence of that vector dotted into the volume. I mean, with respect to the volume. This is called the divergence theorem, which tells you that divergence is equal to kind of, that you can take the divergence of a vector instead and do the volume integral, basically. However, this only happens because the curl of A has to exist. And then the same thing can happen over a surface, right? So if you have a closed surface, A dot ds, that's just equal to basically the curl. So you can kind of go backwards, if that makes sense. So here we're basically moving up a dimension. Here we're moving also up a dimension, I guess. But yeah, and that's Stokes' theorem. And yeah, that's kind of this chapter. I kind of started rambling towards the end because I got tired. But thank you guys for watching. I highly encourage you guys to do some practice problems. I was originally going to, but I'm too tired now. So that's kind of the first chapter, which is really just a bunch of math that's very useful for knowing physics. And I'm going to stop recording now. So see you guys. Peace.